If you spend 30 years in space, lost up to 40% of your bone strength, absorbed radiation levels far beyond a Mars mission, and traveled nearly 6 billion kilometers round trip, would it still be worth it just to reach a planet where you cannot even stand? Uranus is not just far. It is almost 3 billion kilometers away on average. A one-way human mission could take 12 to 15 years. That means 25 to 30 years away from Earth by the time you return. By then, your body would not be the same body that left. Your skeleton could resemble that of someone decades older. Your heart may have shrunk after years without gravity. Your brain would have endured non-stop cosmic radiation in deep space, where there is no natural shield. And here is the part most people never think about. Even if you survive the journey there, the return trip could be even more dangerous. After more than a decade in microgravity, stepping back into Earth gravity could put extreme stress on your bones, muscles, and cardiovascular system. It is not just about reaching Uranus. It is about whether your body can ever come home. We have sent one spacecraft to Uranus. It took over 8 years to get there without carrying a single human being. Now imagine sending a fully loaded crewed spacecraft that must support life for 15 years straight. The scale of the challenge is not science fiction. It is biology, physics, and time working against us. To understand why this mission pushes human limits, we need to begin with distance. Uranus orbits the Sun at roughly 2.9 billion kilometers. Even at its closest approach to Earth, it remains more than 2.5 billion kilometers away. For comparison, Mars at its closest can be around 55 million kilometers from us. That difference is enormous. Mars missions are measured in months or a few years. A Uranus mission is measured in decades. A spacecraft carrying humans cannot travel as lightly as a robotic probe. It must carry oxygen recycling systems, water purification units, food storage, radiation, shielding, medical equipment, spare parts, and propulsion reserves. All of that increases mass. More mass means more fuel. More fuel means even more mass. This is not a simple scaling problem. It becomes an engineering challenge that grows exponentially. Even with optimistic propulsion methods, a crewed mission could realistically take 12 to 15 years one way. That is not a quick expedition. That is a major portion of a human lifetime. The first threat during that journey is radiation. Once a spacecraft leaves Earth's protective magnetic field, it is exposed to galactic cosmic rays and solar particle events. These are high-energy particles that can pass through shielding and damage living cells. On Earth, our atmosphere and magnetic field block most of this radiation. In deep space, protection is limited to whatever shielding we can physically carry. Radiation exposure increases the risk of cancer over time. It can damage DNA directly. Research also suggests it may affect the cardiovascular system and potentially impair cognitive function. Even a Mars round-trip mission, which could last around 2 to 3 years, approaches current astronaut lifetime radiation limits. Multiply that exposure by 10 or more years in deep space, and the cumulative dose becomes a serious concern. This damage is not something that disappears when you land. It accumulates. Each year adds to the total burden on the body. Turning around halfway through the journey does not erase what has already occurred at the cellular level. While radiation works silently, microgravity slowly reshapes the body. On Earth, gravity constantly stresses bones and muscles. This stress signals the body to maintain strength. In space, the constant pull disappears. Astronauts on the International Space Station can lose about 1 to 2% of their bone density per month without countermeasures. Even with strict daily exercise, some bone loss still occurs. Over the course of a decade, that decline becomes significant. Bones may become weaker and more fragile. Muscles, especially in the legs and back, shrink because they no longer support body weight. The heart adapts as well. In microgravity, it does not need to pump blood upward against gravity. Over time, the heart muscle can decrease in mass. When astronauts return to Earth after 6 months in orbit, some experience dizziness or fainting when standing. Their cardiovascular systems must readjust to gravity. Now imagine returning after more than a decade. The readaptation process would be far more intense and uncertain. The psychological dimension adds another layer. Long-term isolation studies on Earth show that confinement can affect mood, sleep patterns, and group dynamics. On a mission to Uranus, communication delays would exceed 2 hours one way. A simple conversation with Earth would involve hours of waiting. Real-time support would not exist. A crew would need to be almost completely autonomous. Small conflicts could escalate in a closed environment. Emotional strain could build over years, while training and preparation help. The duration of this mission would push human resilience further than any previous spaceflight. Assume the crew survives the journey and reaches Uranus. What awaits them? Uranus is classified as an ice giant. It does not have a solid surface like Earth or Mars. Beneath its thick atmosphere lies a deep layer of fluid materials under extreme pressure. There is no stable ground to land on in the traditional sense. The upper atmosphere is extremely cold, with temperatures around -220 degrees Celsius. The atmosphere is primarily hydrogen and helium, with methane contributing to its blue color. There is no breathable oxygen. Any human presence would require a fully enclosed, heavily insulated spacecraft or orbital station. Wind speeds on Uranus can reach hundreds of kilometers per hour. These are powerful atmospheric currents that would challenge structural integrity. The planet also has an unusual tilt of about 98 degrees, causing extreme seasonal patterns. Each pole experiences decades of continuous sunlight, followed by decades of darkness over its 84-year orbit. Its magnetic field is tilted and offset from the planet's center, creating a complex magnetosphere. This irregular field may provide inconsistent protection from charged particles. For a crew already exposed 2 years of deep space radiation, this environment offers little relief. What about Uranus moons? While they may offer solid surfaces, they are also extremely cold and distant from the sun. Any long-term human presence would require significant infrastructure and protection. Now, consider the return journey, another 12 to 15 years in space. By the time the spacecraft approaches Earth again, the crew could have spent 25 to 30 years away. Their bodies would have fully adapted to microgravity. Their bones, muscles, and cardiovascular systems would reflect decades in space. Reintroducing them to Earth gravity could require months of rehabilitation, if recovery is even fully possible. There is also the cumulative radiation exposure to consider. Over such a long mission, the health risks would increase significantly. So why even consider it? Scientifically, Uranus holds valuable clues about planetary formation and the outer solar system. Understanding ice giants helps us interpret many exoplanets discovered around other stars. But these goals do not require human presence. Robotic missions can collect data without risking decades of human health. There are proposals to send an orbiter or an atmospheric probe to Uranus in the future. These missions prioritize science while avoiding the biological costs of human travel. The reality is simple. We evolved under Earth gravity, protected by its atmosphere and magnetic field. Our bones, muscles, and organs are tuned to this environment. When we leave it for short periods, we can adapt and recover. When we leave it for decades, adaptation may come at a permanent cost. Uranus remains one of the most distant and mysterious major planets in our solar system. It is reachable in theory, but for humans, the challenge is not only about propulsion or engineering. It is about whether the human body can withstand 30 years of space and still function on Earth afterward. Reaching Uranus is technically possible. Coming home unchanged is not.